in physics, we're going to see many examples of quantities which we'll refer to as vector fields. Common examples of vector fields are wind, where at every point in space we have the velocity of the air molecule at that point in space. We're going to see in this electromagnetism course two very important examples of fields called electric and magnetic fields. Now, what is a vector field? Well, let's just draw a representation of space. And at every point in space, we'll indicate, here's a point, P1. At this point in space, we may have a vector, v, at that point, P1. Now, what that vector represents is the velocity of an air molecule at that point in space. And suppose we have another point in space, P2, and over here we have the velocity P2. And this represents the velocity at that point, P2. And in fact, we could have another point, P3, and another velocity vector at P3. So what we call a vector field is that at each point, we have a vector, which gives us both direction and magnitude. So a vector field is a collection of vectors, one defined at every point in space. Now, how will we represent that mathematically? Suppose I choose a coordinate system, I hat, j hat, and we'll have k hat. And given this coordinate system, we would now like to represent our vector field v at any point x, y, and z as three components. It can have an x component, I hat, plus a y component, j hat, plus a z component, k hat. So our vector field consists of three functions. In this Cartesian picture, we have the function vx, xy of z, vy, xy of z, and vz, xy of z. And these three functions are how we determine the vector at any point. If I specify the coordinates, say P1 is x1, y1, and z1, then each of these functions defined at the P1 give the components of the vector at the point P1. So from this perspective, a vector field consists of three functions, or another more geometric representation is that at every point in space there's an arrow which describes the quantity that that vector field is describing. In this case, the velocity of an air molecule at point P1. So what we want to do now is also consider that in physics, our vector fields may not just be functions of space, but they also could be changing in time. And let's look at some examples of some vector fields. Let's consider some examples of some vector fields. For instance, again, we'll draw a representation of space like this. And let's draw a vector field that is a uniform vector field. So what I mean by that is in 2 dimensions, at every single point, here's P1, BP1. Every single point in space at P2 and P3, the vector is exactly the same. So in this sense, if I were to refer this to in the I hat direction, then we can describe this vector field, x, y, and z. It only points in the I hat direction, and we can describe that as a constant v I hat. And so this is an example of what we call a uniform vector field. Now, there can be many other types of vector fields. For instance, we might consider one in which that the vectors are all pointing, for instance, if if I were to draw a circle, the vectors on the circle have the same magnitude, but they're changing direction. So in this vector field, it's not a uniform vector field because at every point the vectors are, there is some type of symmetry here, but the vectors are not pointing in the same direction. And these are very interesting vector fields, which we'll look at a little bit later. There can be vector fields, too, which we'll draw at a point, say some center point, where the vector fields, if we drew a circle, instead of pointing tangential, the vector fields point radially inward. And if we went further out, maybe they get a little smaller. And this type of vector field will be characteristic of the electric field of a point charge or a gravitational field associated with a mass centered at that central point. So these examples of vector fields, we'll look at other ones in which if we had a line in space and we drew circles like this, we may have a vector field which is pointing tangent to these circles given this line in space. And this type of vector field will be characteristic of magnetic fields associated with a current in a wire. So we'll be exploring many vector fields in this course,